first met Stephen Phelps. I admire Stephen for many qualities, among them perseverance, search for truth, and a sense of systematic approach. And I believe that by the end of tonight, you will see traces of all these qualities in his talk. Topic of tonight's talk is modern cosmology and the Baha'i faith. Stephen had studied physics at the University of Princeton. He's got his graduate in cosmology and undergraduate in philosophy and physics. Is that right? That's right. And he had served here from 1993 until 1995, where he left to finish his graduate studies, and he returned a year ago, half a year, served back in the research department. So I believe the most important thing that you have to know before tonight. So without further ado, Stephen,
a lot of people when I say I study cosmology, they say, "Oh well, where's your makeup kit?" And the usual reply is, "I study the makeup of the universe, not the universe of makeup." Cosmology is the modern scientific study of the origin and the structure and the evolution of the universe, insofar as it's possible to say definite things about that. It's becoming more and more possible to say definite things about this subject, particularly in the 20th century with the advent of modern astronomy and large telescopes, with the ability now to launch satellites above the atmosphere to make observations which could never be made before, and in general the development of computer technology and other sorts of technologies which are enabling cosmology to basically, particularly in the last few decades, to race forward in terms of the scope and number of discoveries that are being made. And one could say very accurately that cosmology right now is in the middle of a golden age of discovery, and that the best could very well be yet to come in terms of the sorts of discoveries that will be made. But before getting into modern cosmology in particular, I wanted to just say a few remarks to set a little bit of the historical context. Cosmology, of course, is an ancient science, one could say, but science in quotation marks, because for thousands of years, since prehistory, people have wondered about where it all came from and where it's going, one of the most fundamental human questions. And various cultures throughout the world had different mythologies, different sort of creation mythologies. And so up until very recently, cosmology was really the province of theology, of mythology, of philosophy. There were all sorts of different ideas about how it came into being, and really no way to conclusively choose one over the other because of the lack of evidence. One example of this, basically the first major turning point, I suppose, in cosmology happened around 400, 500 BC, and this was in the civilization of ancient Greece, before even Plato and Socrates, with some of the very first, as they're called, pre-Socratic Greek philosophers, some of which you may have heard of, Thales and Empedocles and Pythagoras and so forth. And each one of these philosophers, and there's about 10 of them that you can readily name, whose names at least are fairly famous. And they all had different ideas about the makeup of things. Thales thought everything was made of water, appropriate for tonight. Deluge, I guess. And had his own theory about creation and the structure of things and so forth based upon water. It may not sound like that much of a scientific theory or that much of an advance over a sheer mythology, but one has to credit at least the ancient Greeks for attempting to base their notions of reality upon looking at the world around them and coming to certain conclusions. Even though those conclusions may have been completely wrong as far as the facts are concerned, it was, I think, the spirit of inquiry that was really born in ancient Greece that could be seen as the first turning point in the evolution of cosmology from being just a set of myths into a science. The next major turning point in cosmology, moving the clock forward a couple thousand years, was in the 1600s. And two very significant things happened in the 1600s. One of them from the point of view of the theory, and the other from the point of view of the observations. From the observational point of view, the 1600s actually, that being the 17th century, was the century in which the telescope was discovered or invented by Galileo. And of course, one of the first things he did was point it up to the sky, and he discovered some very interesting things. Among them were the moons of Jupiter, which showed that it's plausible that if these things seem to be rotating around this object up there, then maybe this Earth that we're standing on is also rotating around something else. He looked at the spots on the sun, which was a fairly significant discovery, because up until that time it was thought that everything in the universe, everything up in the heavens was perfect, and that all the rotations of the planets, the motion of the celestial spheres, everything was thought to happen in perfect circles, because the cosmos was supposed to be characterized by utmost geometric perfection. And seeing spots on the sun was quite a shock to some people, because the sun is supposed to be one of these perfect heavenly bodies. And so Galileo's discoveries helped very much to dislodge our thinking from that sort of flat Earth-centered thought into one in which the notion that the Earth was round, that it revolved around the sun and not the other way around, and so forth, gradually became established facts. Now, from ancient times, it was known that the planets orbited. Well, it wasn't known that they orbited around the sun, but it was seen that certain stars in the sky wandered. These are the ones that didn't twinkle, because actually this is what the difference between a star and a planet is. Stars twinkle and planets don't twinkle. And the reason for that is that the planets are so close that actually the disks, the sort of finite size of the disks of the planet means that the starlight doesn't get interrupted by the atmosphere as it does the stars. So it was noticed that these wandering stars wandered in very definite cycles, whose rhythms could be counted according to a precise number of years and a precise number of days. And even when they really got down to the details, they could, down to the number of hours, because it was known even to the ancients that to some of the ancients at least, that the orbital period of the Earth is not exactly 365 days, and it was known, for instance, that the Earth sort of precesses on its axis, and so the North Star is different from age to age on a period of something like 36,000 years. I can't remember the exact number, but the pole star actually precesses. But these motions, which are so small, on the level of a human lifetime, you would never notice anything. But the ancients were, even without the assistance of telescopes, were able to make these observations and know that there's certain sort of universal cycles up there. Anyway, but it wasn't known what the laws, the structure of the laws that caused these cycles was not known. They could do the numbers, they could calculate things, they could come up with elaborate charts, they could predict where the star would be 10 years from now, or this planet would be 10 years from now, and so forth. But it wasn't known what the laws that they followed were. And this is where the second main advance of the 17th century came in, and that was with Isaac Newton's discovery of the universal law of gravitation, embodied in his Principia Mathematica, which not only introduced this universal law of gravitation, but also introduced for the first time the concepts of force and mass and acceleration. Those of you who have studied a little bit of physics in college or even in high school might be familiar with Newton's laws of motion. There's 3 laws of motion that he came up with. And the combination of these 3 laws of motion plus this universal law of gravitation, with this combination with this mathematical arsenal, one could then show why it was that the planets were doing what they were doing. One could derive from the law of gravity the motions of these planets, discover, for instance, that they did not move in perfect circles, but they moved in ellipses, and other facts about astronomical facts. So these were great advances in terms of our understanding of the cosmos around us. But still, if one were to ask the question in the 17th century, well, where did it all come from? What about beyond the planets? What are the stars really? No one would really know the answer to that. No one would have any idea how far away they were, how big the universe was. It was still very much unknown. And this realm of cosmology, as opposed to what I've been describing, which is more astrophysics or even planetary science, the realm of cosmology was still very much a terra incognita. It was a completely unknown field. So it had to wait until the very early part of the 20th century before cosmology could be established on a firm foundation as a modern science. And again, there were 2 hand-in-hand developments that allowed this to happen, one on the theoretical side and one on the observational side. From the observational side, it was the creation of massive telescopes using the same principles as Galileo's telescope, but just on a very large scale. And these telescopes were, one of them was on Mount Palomar in California. One of them was there was a few of them, I can't remember all the names of them, very famous objects, because at the time they cost huge amounts of money, and a lot of people wondered why they were building them and what good it would do us and so forth. But once these huge telescopes were created and they started pointing them up at the stars again, they saw in detail never before seen certain objects that before it wasn't known what they were, but now they could start coming up with some ideas about what they were. They started seeing these fuzzy patches. What to the naked eye may have been fuzzy patches, or to Galileo's telescopes would have just been these sort of oblong clouds that never seemed to disperse. In the sight of these huge telescopes could be seen to be their own sort of island universes almost. They seemed to be comprised of stars. Some of them had their own structure. Some of them had these spiral structures and looked like they might be in the middle of turning around and so forth. And it was realized for the first time, and this was in the 1910s and 1920s, it was realized for the first time that we ourselves live inside one of these island universes, later to be known as galaxies, and that outside our own galaxy were an uncountable number of other galaxies of various shapes and sizes and distances and so forth. And this signaled another significant shift in our view of where we were in the cosmos, whereas it was already a big step to move from the notion of the Earth being the center of everything and the Sun and all the other planets revolving around the Earth. That view at least had been corrected, and now we could see that the Earth revolved around the Sun, and the Sun was more properly the center of our solar system. But you could still argue that the solar system was sort of the center of things. But now with these new observations, there was no longer any denying the fact that we lived as just a single mote or a speck of dust almost in this vast ocean of other specks of dust, which were the other galaxies. A second, again in terms of observations, a second very significant observation was made, and this has to do again with the use of telescopes, but with using these telescopes in a different way. All light that comes from these galaxies is not just white light. It's comprised of different frequencies or different wavelengths, different colors of light, all mixed together. And when you look at it, it looks like a particular color. But with a particular scientific instrument called a spectroscope, you can actually split that light into all of its component colors. And the science of spectroscopy was just developed in the early 20th century. And they used these spectroscopes on these galaxies. And they discovered something very significant. They found when they split the light from these galaxies, they could see certain bands where there wasn't any light. Light would be emitted in a certain range of frequencies, but there would be particular frequencies where there wouldn't be any light emitted. And these frequencies, these particular frequencies, which are called absorption lines in the parlance of spectroscopy, signified the presence of particular elements in these galaxies. And the reason why it does that is that particular elements, say hydrogen or helium, tend to emit radiation and absorb radiation or light of very specific frequencies. And so the existence of these absorption lines in galaxies outside of our own was proof to people that these other galaxies were essentially made of the same stuff as ours. That is, they're essentially made of the same elements, hydrogen and helium for the most part, with a few other trace elements. But there is a very subtle difference in the spectra from these outside galaxies, and that is that although the spacing of these absorption lines was the same in all the galaxies, different galaxies had their absorption lines shifted over to one side or another a little bit. And most of them were shifted over to one particular side. And that side was towards the red end of the spectrum, or towards the longer wavelength end of the spectrum. What had been discovered, and it was Edwin Hubble, the astronomer after whom the current Hubble Space Telescope is named. It was Edwin Hubble who discovered this, and it became known as the cosmological redshift. What it means is that every single galaxy that we can see, with the exception of a very few nearby galaxies, is redshifted. And the explanation of this redshift, the only plausible explanation that anyone has been able to come up with, is that the redshift results from the fact that the galaxy is moving away from us, or that we're moving away from it. But since the galaxy on this side of us and the galaxy on this side of us are all moving away from us, it gives the picture that every galaxy in the universe is somehow being repelled away from us. But not only that the galaxies which tended to be fainter and smaller, and therefore farther away, were redshifted even more. In other words, the farther away a galaxy was, the faster away from us it seemed to be moving. And there were two possible explanations for this. One explanation is, we're at the center of the universe, and everything is moving away from us for some reason. But people didn't really want to believe that we were really at the center of the universe, because it just didn't seem like it was the case. Everything else out there looked pretty much the same as it was here, and why should we be any more special than any other place in the universe? So the other possibility, which was inevitably the one that was adopted, was that, well, it must be the case that the entire universe is expanding, and that the reason it seems that the expansion is proceeding from our point, which is stationary, is that basically space is expanding everywhere at the same time, at the same pace. One way to envision this is to have a balloon, and was a balloon ever... They said, "Do you need injured?" I said, "Just give me a balloon." They thought I was joking. You actually need a balloon for this. But, well, you can imagine blowing up a balloon and putting a bunch of spots on the balloon and then blowing up the balloon. And the spots on the surface of the balloon, every spot moves away from every other spot. So if you focus in on one particular spot on this balloon as you're blowing up the balloon, then you'll find that every single other spot on the surface of the balloon is moving farther and farther away from this one spot. And you can pick any spot on the balloon, and you're going to see the same thing. And so this expanding balloon analogy, which has its limitations, as I'll get into a little bit later, is at least useful from the point of view of imagining that if our universe is just expanding, going up by one more dimension, that our universe, our three-dimensional universe, can be compared to the two-dimensional skin of a balloon as it's expanding. So that's how, that's the modern theory about that's the evidence for the expansion of the universe, and that's the theory behind it, that essentially every point in space is moving. It's as if you can divide space into a sort of a series of grid points. Picture, like a Cartesian coordinate system, the vertical and horizontal grid points, and bring that into three dimensions. And so you can picture space as being filled with these invisible grid lines. And to identify any point in space, all you have to do is count the number of grid lines over this way, and count the number of grid lines vertically, and count the number of grid lines horizontally, all three directions, and you can come up with a unique point in space. That's one way of sort of parsing space. But the fact that space is expanding means that all the grid lines are getting farther away from each other. In other words, your standard measure, the standard distance between one grid line and the next, is increasing with time, almost imperceptibly. I mean, certainly at the scale of the planet Earth, it's absolutely imperceptible. At the scale of our solar system, it's imperceptible. At the scale of our own galaxy, it's even barely perceptible. It's not actually perceptible at all because the gravitational pull of the stars in the galaxy are enough to offset this expansion. In other words, the galaxy itself is not getting bigger because gravity is holding the galaxy into a particular size, but it's the space between the galaxies that's sort of expanding. So this is the theory of the expanding, sort of the expansion of space. It leads immediately to several questions, and one is, well, if space is expanding, then if you go back in time, it must have been getting smaller and smaller, and then what happens then? And then that leads us to the subject of the Big Bang. But before I get to the subject of the Big Bang, I want to talk briefly about the second major, this was all the first major sort of advance of the 20th century, this discovery of the expansion of the universe from observations of galaxies. And the second major advance at the beginning of the 20th century that allowed cosmology to be placed upon a solid footing, a solid scientific footing, was Albert Einstein's discovery of the general theory of relativity. Everyone is at least familiar with the equation E equals mc squared, which is one of the basic equations in the special theory of relativity. The general relativity theory of relativity is something quite different. Einstein was responsible for two absolutely amazing theories. I mean, if he only did one of these, he would still be considered one of the most brilliant physicists of all time. But he came up with, well, not only the special and the general theories of relativity, but also he made theoretical advances towards quantum mechanics that also equally would have earned him a place in the annals of science. If one were to really count up the major advances that Einstein has made in science, it really surpasses anyone else. So anyway, the special theory of relativity, just briefly, is the theory that results when one makes the assumption that the speed of light is a constant. Everything else in the theory of special relativity follows from the assumption that the speed of light is a constant, and the assumption that the laws of physics appear to be the same in whatever reference frame you're in. In other words, people moving at constant velocities relative to each other should have the same fundamental observations about the laws of physics. So with these two assumptions, the special theory of relativity sort of falls naturally into place. The general theory of relativity, and so the special theory of relativity basically tells us how space and time are related. It tells us that actually space and time are not two completely separate things. Well, if you can even call them things, they're not two completely separate concepts. But depending upon the velocity of one observer with respect to the other, what they think of as space and time becomes a little bit fuzzy. So that someone moving very quickly relative to you is going to experience space very differently than you will. They'll experience space to be contracted, and they'll experience time to be expanded or lengthened, drawn out, relative to events that you might observe. So this is all special relativity, and I'm not going to get into that. It's general relativity that really is the foundation of modern cosmology, and everything that cosmologists do is based upon this theory. And the theory basically began with the idea, which Einstein I think later called one of the most beautiful ideas of his life, which is a very simple idea, and that is that a falling object does not feel its own weight. So he said, if someone, for instance, is in an elevator, a very long, tall elevator, and the cable to the elevator snaps, and he finds himself in free fall. But he's in an elevator, so he can't see the world outside, and he can't see that he's going very fast. And it's a completely isolated elevator. All he's going to notice is that suddenly he feels weightless. And those of us on Earth interpret weightlessness as a sign of falling. But that's what he would feel. And in the absence of any sort of external stimuli from outside this elevator, he's just basically going to be under the impression that he suddenly became weightless. Likewise, an astronaut on the space shuttle orbiting the Earth feels weightless too. And the two people, the guy in the elevator who's free falling towards the center of the Earth, and the guy who's in orbit around the Earth, are both weightless. And the reasons why they're weightless, Einstein said, are basically the same. I mean, it's not that one is falling and the other isn't. It's that, to try to put some clarity into it, that a gravitational field like the Earth basically curves space-time. And that the path you follow, if you're not under the influence of external forces, is one that basically follows a geodesic in this space-time. A geodesic is basically the shortest distance between 2 points on a curved surface. But that's not important for what follows. Basically, what's important is that the general theory of relativity posited for the first time the mathematical relationship between mass and curvature of space. And it's a very simple equation. If you want to write down the equation, it basically says that you have an entity called the curvature tensor, which is complicated in itself, but when you write it down as an equation, it's just one letter, is equal to 8 times pi times this other letter, which is basically equivalent to the mass energy constant of the universe. So it's a sort of an A equals B type form. It's a very simple equation. Actually solving it is very difficult. But conceptually, at this level, conceptually, it's a simple idea. It's that mass or matter or energy causes the curvature of space-time in the proportion of 8 pi. And why 8 pi? It's 8 pi because general relativity is so constructed that in the limits of very small masses, where space-time is not curved that much, it ought to end up approximating Newton's theory of gravity. That is, Newton's theory of universal gravitation is a special case of Einstein's theory of general relativity. On Earth, Newton's theory of gravity is good enough for anything we do. The scientists at NASA don't have to use general relativity to plot the course of the space shuttle. They use plain old Newtonian physics. Only when you're talking about black holes and galaxy recession and the sort of the big picture of the expansion of the universe do you have to worry about things like general relativity. Okay, so that's those are the two main elements that went into the foundation of modern cosmology as a science today. Now, what can we say are some of the basic ideas? So, what are the sort of foundational pillars of modern cosmology? I'll just list off a few of them, but the principal ones. The first one, as we've already discussed, is that the universe is expanding. We know it's expanding because A, all the universes are moving away from us, and B, it's somewhat ridiculous to assume that we're at the center of the universe and that they're all just sort of running away from us. The expansion of the universe, however, it's not that the universe is expanding into something, and this is a point that has to be made clear. Because when you think of like the expanding balloon, and this is where the expanding balloon analogy really gets your thinking going in the wrong direction. Because when you blow up a balloon, the surface of this balloon sort of wraps around itself. So if you go on the surface of the balloon long enough, you'll end up at the point you came from if you walk long enough along the surface. It's not necessarily the case with the universe that it's this closed sphere in four-dimensional space. The universe is not necessarily a hypersphere. That's only the case if the curvature of the overall curvature of the universe is closed, which is, scientifically speaking, technically an open question, although the preponderance of the evidence to date very strongly suggests that it's not closed. In other words, it's not the case that if you keep going in one direction, you're going to end up back at the Milky Way. Yeah. A hypersphere is a four-dimensional sphere. It's basically a sphere. It's like a regular sphere, but add one more dimension to it. A hypersphere is to a sphere as a sphere is to a circle. So if you can picture moving from a circle to a sphere by sort of rotating it in another dimension, then you can move from a sphere to a hypersphere by rotating the sphere in the fourth dimension. You can do the same thing with a cube, by the way. A square sort of moved in a third dimension becomes a cube, and that cube moved in a fourth dimension becomes a hypercube, also known as a tesseract for people who have read Madeleine L'Engle's Swiftly Tilting Planet. Anyone read that? It was good like fiction when I was in junior high school. I've just dated myself. Okay, so space is expanding, but it's not necessarily expanding into something. It's just that the fabric of space-time itself is a dynamic entity, and the expansion of the universe has to do with the way you measure distances between things. It's not the fact that there's a void out there and space is moving into it. Because that would also lead to the notion that there's an edge of the universe somewhere. But there is no edge of the universe as far as we know, at least. So space is not just a static receptacle for things, but space itself partakes of Einstein's equations. It is warped and curved by massive objects, and so it sort of has a life of its own. Very different from the old Newtonian view that space is simply emptiness, and that the only thing that matters are the objects you put in it and the forces between them. The 20th century view of space is that it itself is a sort of a fabric. It's not made of anything physical at least, but rather it has, it itself can fold in on itself, it can curve, it can do whatever in reaction to matter. So that's the first sort of pillar of modern cosmology, one could say, that the universe is expanding. The second is that this expansion proceeded from a hot initial stage, a very hot, dense initial stage, which is popularly known as the Big Bang. The Big Bang was originally a term given by Fred Hoyle, who didn't believe in it, and gave it this term to ridicule it. But it caught on, and so everyone calls it the Big Bang now, and it's lost its original pejorative connotation. So how do we know for sure that this expansion proceeded from an initial hot, dense state? There are two very solid pieces of evidence that lead cosmologists to believe this is the case. The first piece of evidence is that if you look at the overall sort of cosmic elemental abundances of things, you'll find by looking at these spectral lines, you'll find that the universe is made up of about 75% hydrogen, about 23% helium, and about 2% everything else. Hydrogen and helium, of course, are quite rare elements on the Earth. We're surrounded by just about everything but hydrogen and helium. And so despite the fact that the elements we're used to on a day-to-day basis seem very common to us, on a cosmic scale, carbon and silicon and oxygen and all these things are quite rare. They form a very small fraction of the content of the universe. And by the way, the remaining 2% I think is mostly iron, because iron is sort of what's created in the cores of stars when they go nova, and that's sort of everything burns its way to iron. So everything else, the carbon and everything we're made of, and all these other elements are basically the chance, one could say, the chance byproducts of the death of stars. As they've burned away their nuclear fuel and gradually sort of succumb to their own gravity, and then more higher and higher elements become fused together through this process, and ultimately the core of the star sort of reaches the point where it fuses into iron, and at that point, and through all this process of fusing into higher and higher elements, energy is released, and that energy in the form of heat keeps the star from collapsing. But once it reaches iron, it can't fuse anymore, because you can't get any more energy. In terms of nuclear physics, you can't get any more energy from fusing elements beyond iron. And so it stops, and then the star suffers catastrophic collapse, and then it explodes. And the reason why it explodes is that when the collapse reaches a high enough state, then it basically shoves the electrons onto the nuclei, and it creates a sort of a core of neutrons, or a core of there are different things. There are different stages in the death of the star depending on the mass of the star. It can do all sorts of interesting things. In the most extreme cases, it can become a black hole from which not even light can escape, because the density of the remaining star is so high. But I'm not getting into black holes or neutron stars or anything either, because that's really more properly the subject of astrophysics, which could be the subject of a different talk. But I have to get back to cosmology. So back to cosmology, how do we know that the universe started at a Big Bang? How do we know that everything began very hot and dense? So we have knowledge of these elemental abundances, and there's no rational explanation for the fact that the universe is about 3/4 hydrogen and 1/4 helium, with a few other things. No one has been able to come up with a better explanation why this is so, other than the Big Bang. Because in the Big Bang, as the universe expands and cools from this initial very hot, very dense state, in which not even atoms can survive, it's only a sort of a quark soup. Atoms, protons, neutrons make up the nuclei, and electrons rotate around the neutrons, but the nuclei themselves are made up of quarks, three different kinds of quarks. This is the modern physics theory of the constituent, the sort of building blocks of matter. And I unfortunately don't have time to get into quarks and all that sort of thing, which is another interesting topic. But so at the very beginning, everything was just sort of a quark soup, because that's the only thing that could survive. And ultimately, it cooled down, and the quarks sort of glommed onto each other and became protons and neutrons, and the electrons were around there too, and neutrinos and these other sorts of things. And then, as things expanded more than these protons, the electrons finally joined into the protons, and the neutrons. There weren't that many neutrons, but some of the neutrons went to glom onto other neutrons and a couple other protons, and they would form helium nuclei, and other protons would just go along, and they would glom onto an electron and become a hydrogen atom. Basically, if you go through the numbers, if you look at what the densities were, if you look at how much time they would have had to interact, which is about 3 minutes. Actually, most of the early history of the universe took place in 3 minutes. Most of the exciting stuff took place in 3 minutes. And it's one of the great monuments to the human intellect that scientists have been able to extrapolate, all using laws of physics that everyone knows and loves and learns in college and high school and so forth. You can use these laws of physics and extrapolate all the way back to about 10 to the minus 12 seconds after the Big Bang. No one can actually go all the way to the Big Bang because then the density becomes infinite. When the density becomes infinite, all the equations break down. The laws of physics as we know it no longer exist, and it's no longer possible to make scientific predictions about what's happening because you no longer have the equations. But you can go all the way up to a fraction of a fraction of a fraction of a second right after the Big Bang. And what happens is you have the quarks that eventually sort of coalesce into atoms and so forth. These atoms, if you go through the numbers, you find that most of the atoms are going to be hydrogen, and that a smaller fraction are going to be helium, with tiny, tiny trace elements after that. And if you look at the fraction of hydrogen to helium predicted by the Big Bang theory, it's equal to the abundances that are actually observed. So that's a very significant piece of observational evidence for the Big Bang. Now, of course, there are different sorts of parameters you can throw into the theory that can give it different abundances, but these other parameters are constrained by other observations. So what you have is a network of closely intertwined observations, all of them sort of casting light on a different part of the theory. And if you want to change the theory a little bit, then you have to account for all these different sets of observations. And currently, the only theory that meets all of the observations simultaneously is this Big Bang theory.
What did you say about a fraction?
A fraction of...
You said the fraction of these that were observed and had two fractions at the biggest.
Yeah, so the fraction of hydrogen to helium predicted in the theory is about 3 to 1. And the fraction of hydrogen to helium that we actually observe through the spectral lines of galaxies is also about 3 to 1. Now, it's complicated by the fact that stars are burning up hydrogen all the time into helium. So the actual abundance of helium that we measure has to be higher than the primordial abundance, because some fraction of the helium we see is a product of stellar processes of fusion in the stars and not the primordial nucleosynthesis. And so that it adds to the complication of it. And so just the primordial element abundances alone would not be sufficient to prove the Big Bang theory. There have to be different lines of evidence. Another line of evidence is the microwave background radiation. And basically, many of you might have heard about it, read about it in articles, popular science, and so forth. Particularly in 1992, it was all over in the headlines that the scientists finally proved the Big Bang using satellites. And what these satellites did was they were looking at a particular frequency of light. And this frequency of light corresponded to the sort of afterglow of this initial explosion of the Big Bang. If the universe began in a very hot, dense state, then just like a light bulb, if something is hot, it glows. And the frequency of light that it glows in is a very specific frequency. It's called the black body spectrum. And this spectrum of light is something that is found in every single hot object that science has ever looked at. And the shape of the spectrum can also be derived on fundamental principles and as a result of quantum mechanics. But so you have this black body spectrum. If that you're looking for. If the universe began in a hot, dense state, then as it expanded and this black body spectrum cooled, then you could calculate exactly where you expect to find this spectrum today. In other words, where you expect to find this afterglow of the Big Bang. At what temperature you expect to find it. And the theory predicted that it would be right around 3 degrees above absolute zero. In other words, it's pretty much cooled off. But still, there's enough energy left from the Big Bang. There's enough of a glow left from the Big Bang that it's detectable using very sensitive microwave, and it's in the microwaves, by the way. The same microwaves used to cook your food, but much lower intensity. We're surrounded by these cosmic microwaves. If you turn on your TV and you turn it to a station where there is no station, you just see the snow. A fraction, 5%, whatever, some percent of that snow that you see is actually cosmic microwave backgrounds. Because TV broadcasts in the microwave range. and so some of the microwaves sort of impinge on TV reception. So these microwaves then were measured very carefully by satellite experiments, and it was found to correspond exactly to a black body spectrum at exactly the temperature they were looking for. So this discovery of the microwave background was considered the single most strong piece of evidence for the fact, or for the theory, I should say, that the universe began in this hot, dense state. The single strongest piece of evidence for the Big Bang. So to summarize, the evidence for the Big Bang is, first of all, the expansion of the galaxies. And if the galaxies are expanding, it's just a matter of extrapolating back in time to say they must have expanded from something, or from some initial state. Secondly, the sort of primordial elemental abundances. And thirdly, from the microwave background spectrum. So, how big is the universe? This is a little bit of a shift, but it's related to the fact that if it's expanding, well, if it's not expanding into anything, then what can you say about its volume? What can you say about its size? And particularly, if it has a finite size now, well, if it started at a sort of a point, then you'd think it must have had a finite volume back then, and so now it must also have a finite volume, because if it's expanding at a finite speed, then it can't have an infinite volume, you might think. but it actually has an infinite volume. Well, I'll moderate that and say it is thought to have an infinite volume. If the matter in this universe is the kind of matter we think it is, and even if we give ourselves a bit of leeway and say maybe we're off by a factor of 10 in the amount of matter in the universe, and that what we think is there is really 10% of what's really there, even that much more matter is not enough to reverse the expansion. In other words, it's expanding so quickly that it would take more matter than there is in the universe in order to reverse the expansion and cause it to contract. And this, the amount of matter in the universe and whether it continues to expand or contract is crucially connected to the overall geometry of the universe. That is, if it's going to continue to the expansion goes on forever, then that's often related to or connected to the notion of an infinite size for the universe. To try to put this in other terms, measurements have been made of the overall geometry or curvature of the universe, and that curvature looks like it's flat, Cartesian. In other words, it doesn't look like there's any curvature. It doesn't look like it's a balloon in 3 dimensions. It doesn't look like, and you can think of another, you can't really think of it, but you can turn a balloon inside out, and that would be a negative curvature surface, like the point on a saddle, where you have the sort of, it goes down this way and it sort of goes up this way, and on the point of a saddle, that's the point of negative surface curvature. If you can somehow picture this saddle point applying in a 4-dimensional object at every point in space, then you've managed to picture space with negative curvature. No one I know can do that. But it appears that it might be the case that either space is negatively curved or it's flat. In either case, it has infinite volume. And if it has infinite volume, that has very interesting consequences. First of all, if it has infinite volume, and if the universe everywhere looks about the same, and I left this out, I should have said this at the very beginning, that the foundational assumption of modern cosmology is what's called the cosmological principle, which is the statement that, to put it in one way, we don't live in any special place in the universe. That is, the universe looks pretty much the same. Wherever in the universe you are, you're going to see pretty much the same thing. You may see of course you'll see different constellations, different patterns of galaxies, and so forth, but on the largest scales, the universe pretty much looks the same from every direction. It's the assumption that the universe is homogeneous and isotropic on large scales. Those are the technical terms for it. So,
is that because that fits into a humanist philosophy better
homogeneous and that we're not at the center of the universe?
Well, not that there's differentiation in spatiality.
In what?
In the universe. I mean, why would we necessarily assume that it's homogeneous fundamentally unless we philosophically wanted to believe that?
Well, one reason to assume it's homogeneous on a large scale is that if you don't assume that, you can't do cosmology. So there's a very practical reason. If you want cosmology as a science, the only way you're going to get it is if you make this assumption that the universe pretty much looks the same everywhere. Otherwise, you have no way of making these sort of global statements.
Point, there's no way of testing that.
Yeah. But there's no way of proving it in the sense of a logical, Aristotelian, crisp, chaste, series of proofs that lead you inevitably to the conclusion. You can't do that with any science. Certainly not with cosmology, let alone any other science. And that's one thing that we won't be able to prove as long as we're stuck on the Earth, and that is this assumption that we've made that the universe tends to look the same from any direction, from any location.
It's a functional assumption.
It's in part a functional assumption, but it's also most people would say it's more than just for convenience. It's more than just an assumption of convenience, but it's also one of. It would be odd to think that we are special, because we know enough about our own planet and our own star and our own galaxy to know that these aren't very special, because we can look out and see these other galaxies that look pretty much the same as what we think ours looks like, and other stars that are a lot more interesting than our star. And our star is a pretty average star as far as stars are concerned. But there doesn't seem to be anything special about our particular location. And so that's the assumption that's made. Under this assumption, we have this wonderful science of cosmology. And what the science is telling us is that the universe probably is infinite in its volume. And so when you read, for instance, in popular articles and so forth, they say the galaxy contains 100 billion stars and there are 100 billion galaxies in the universe. Sometimes you'll see this sort of thing. Don't believe it, because the universe has a lot more than 100 billion galaxies, if the current theory is correct. It actually has an infinite number of galaxies. And the reason why people say 100 billion is because that's maybe about the number of galaxies we're able to see. Because you look far enough back in time, and you're looking back basically. Whenever you look outside, the farther you look back, the farther you look out into the universe, the farther back in time you're looking. And so there's a limit. It's called the event horizon of the universe, basically, or the cosmic. I can't remember. There's two different terms. I think it's called the event horizon of the universe, or the cosmic horizon. There's a certain distance beyond which you cannot look, because the Big Bang. Because beyond that, you're looking before the point of the Big Bang. And the fact that there is a cosmic horizon doesn't contradict the fact that the universe is infinite in extent. It just means that that the visible light that we can see is like the lamppost in a dark on a dark street corner. And you stand underneath the lamppost, and this light sheds light in a certain radius. And you can say, well, the area covered by this light is such and so, and there are X numbers of rocks in this area, and there's you can sort of catalog what's in this sphere of light cast by this lamppost. But of course, there's all the rest of the world past the light of the lamppost, and that's the same case with the universe. That we can see, we can extrapolate. Maybe there are about 100 billion galaxies within their sort of visible cosmic horizon, but if the current generation of observations is correct, it's actually infinite in extent.
Well, somebody would take exception to it if you said 106.
Yeah.
Just round roll.
Okay, so there are some outstanding problems in cosmology. No cosmologist presumes to to say that it's all wrapped up and we know the answers. There's many significant unanswered questions. Among them are, where did the Big Bang come from? No one knows the answer to this. There are a lot of very interesting theories, which we don't have time to get into. Some of the theories are that this universe is like a bubble almost, an expanding bubble, like in a soda glass or something, and you sit there and you watch a soda glass, and these bubbles seem to appear out of nowhere, and they sort of expand and on their way up, and then they go to the surface and then they pop. Maybe our universe is the same. It's just sort of, it's a bubble that sort of appeared out of this matrix of something else, and it's going to have its own light, and whether it eventually collapses or keeps expanding isn't really fundamental to that theory. But what is fundamental to that theory is that if there's one bubble, there's probably an infinite number of other bubbles. In other words, what we think of as being the universe may only be one tiny speck or one bubble in an infinite series of other universes to which we don't even in principle have any access to. We can never observe them because light can never reach us from them. They're sort of closed off to us in this life anyway. That's one sort of current theory of the Big Bang. The big fizz. Another major outstanding question in cosmology is no one really knows what the universe is made of. In terms of matter, in terms of, as it's called, baryonic matter, that is matter made of protons and neutrons and so forth, we know that it's mostly hydrogen and some helium and so forth. But when you look at the large-scale motions of galaxies, when you look at clusters of galaxies and how they move internally to the cluster, when you look at gravitational lenses and all sorts of other astronomical objects, there are various ways of gauging the mass content of structures on a cosmological scale, and all of these are pointing to the fact that there's a lot more mass in galaxy clusters and in galaxies themselves, the rotation curves of galaxies. There's a lot more mass in these objects than can be accounted for by the mere cataloging of luminous matter in the stars and the sort of uncollapsed hydrogen and stuff that's in between the stars. Even if you give very generous estimates about the amount of gas that's just sort of wandering, that's just sort of in between the stars, you can only put in so much gas before you can't see the stars anymore. So there's a limit to the amount of hydrogen, helium gases that can be in the galaxy. But the observations are telling us that there's 10 times more matter in the galaxy than we can see. No one to this date knows what this matter is made of. It's called dark matter because it doesn't cast any light, and its identity is unknown. There are a lot of theories for what this dark matter may be. Exotic new particles. It could be maybe brown dwarfs. I mean, there's some theories that it's exotic matter. A brown dwarf, by the way, is a partially collapsed star that didn't collapse all the way, or that didn't really get ignited all the way. It's like something in between Jupiter and the Sun that's big enough to sort of not be a planet, but not big enough to really be a star. So some people think most of the matter is maybe locked up in these objects, and you can't see them, and so. But there's other reasons not to think that's the case. There's some reasons to think it is the case. There's some reasons. So you have cosmologists, all sorts of cosmologists, going on different tracks and saying, well, I think it's maybe this, and this team thinks maybe it's this, and this team thinks maybe it's this. And that's the nature of science, sort of at the cutting edge, at the very forefront, where no one knows the answers yet. But everyone at least has this common set of theories that they can agree on. You know, the idea that the universe follows physical law, that these laws are described by general relativity, that the Big Bang theory, you know, is more or less correct, even though there are different versions of it that may end up coming out on top. But it's not known what the mass content is. It's not known what its ultimate fate will be yet. And this is again one of the holy grails of cosmology. Is we want to know how the world is going to end. Right around in the mid 1920s, when cosmologists were first solving the equations of general relativity, and coming up with the fact that the universe could keep expanding or it could collapse. For the first time, it was known that these are the sort of possibilities for the fate of the universe. Robert Frost was around, and he wrote this great poem in 1923. He said, "Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction ice is also great and would suffice." So it's still an open question whether it's going to be fire or ice. It's thought it's probably going to be ice at the moment. Okay. So are there any questions at this point? Do you want to break? Because then the next part is bringing in some of the Baha'i writings.
I guess it's a technical question, and that, I've read some of these things you've gone over.
Mm-hmm.
Is at that very beginning, the Big Bang, what created the momentum or velocity? Maybe I'm using the wrong terminology. My thinking is, well, if everything's so jammed together, wouldn't the gravity keep it from expanding?
Yeah.
And I know it has something to do with the curvature and all this other stuff. But maybe why didn't it just fall back on itself right there?
That's actually, it's an excellent question. If there's all this matter compressed like this, matter has a tendency to attract other bits of matter, and that's what gravity is all about. And so it's a little bit counterintuitive to suppose that there was any expansion in the first place. And to explain that, one has to get into what's called inflation theory. The theory of inflation was invented by a physicist named Alan Guth at Pennsylvania State University in 1980. Very recent theory. It caught on like wildfire, and a lot of people believe it. A lot of cosmologists, 70-80% of cosmologists probably adhere to at least believe some form of inflation theory right around. Basically, inflation theory states that it's difficult to explain, but basically that there is, if you take out all the matter in the universe, so that there's no matter whatsoever, the idea is there's still an energy density locked into space. Some sort of positive energy associated with space itself, in the absence of everything else, in the absence of light, in the absence of whatever. There's some just intrinsic energy component to space. And if you do the equations, if you calculate, if you take a volume of this sort of empty space that just has this sort of positive energy component, and you ask, well, is it going to be a tendency to expand or contract? The answer is it's going to want to expand. And it's going to expand, not only is it going to expand, but it's going to expand exponentially. Mm-hmm. And so that in the space of 10 to the minus 43 seconds or something like that, the universe will have expanded. This is before, the inflation theory, by the way, is before Big Bang Theory even starts. So sort of you have this period of inflation, and then the Big Bang Theory itself sort of takes over. Inflation theory sort of jump-starts the process, and then the sort of traditional Big Bang physics comes in. So basically, it's the idea that there is some energy component, which is called the inflaton field. And this inflaton field, it's ready to explain everything by new terms, which really don't explain anything. But so this field basically is thought of as responsible for the expansion. Basically, it means that any space in which there's a intrinsic positive energy component is going to expand exponentially. So that's thought to account for the expansion of space. So any other questions at this point about? Do you just want me to stop at this point, or yes?
I have a question about what you said about the universe being flat. I guess I just visualize things. So I'm trying to visualize this as there's like infinite amount of galaxies, etc., but it's flat. You know, I'm
flat.
Like,
okay, by flat.
How do you visualize that yourself? Like,
not flat as a piece of paper, but flat as. Okay, if you picture this balloon, and you blow up the balloon, and you keep blowing up the balloon until it's bigger and bigger and bigger and bigger and bigger, until the balloon is like as big as the Earth. And you're standing on this balloon, and as far as the eye can see, it is as flat as a pancake. But if you step back enough steps, it's actually got curvature to it, and it's actually curved. So by space being flat is the sort of the same thing. It's the same sort of thing that I'm trying to say. That there may be some curvature, a little curvature associated with it, but on the whole, there's no sort of. The distance between 2 points is always going to be a straight line. Let's just leave that as the definition of flat space. It means the distance between 2 points is always going to be a straight line. And not all spaces is that going to be the case. If on the surface of a globe, the distance between 2 points is going to be a curved line. So maybe that's one way of thinking.
But the space between the galaxies and
is just straight, flat. Yeah. Yeah.
Background cosmic radiation, you said it's only about 3 degrees Kelvin.
Yeah.
So that means it's pretty cold. It's very low in energy. What causes the galaxies to still repel each other or not repel each other? What causes the universe to expand?
Well, it's
the energy is so little.
It's the expansion of the universe is not caused by the microwave background radiation. It's not the energy locked in that sort of echoes of the Big Bang that drives the expansion process.
It's that inflation.
It's the inflaton field and the sort of momentum created from this initial expansion, which the combined mass of the universe is unable to reverse. So
like in zoology, you call it instinct, but you can't explain it.
An instinct.
At least with inflation, you can write down equations. If we assume this, then it follows from the equations. The question is explaining what is this inflaton field, trying to motivate what this thing is in terms of some other fundamental law. And inflation is not yet well motivated. In fact, inflation tends to run contrary to another major modern theory of physics, which is string theory. And inflation theory and string theory don't really get along, but they're both sort of these avant-garde notions in theoretical physics in their various fields. And as time goes on, they're going to have to eventually sort of face each other. And it's also the case with general relativity and quantum mechanics. General relativity and quantum mechanics do not get along as theories. They're incompatible. Fortunately, general relativity only applies at really large scales with really large masses, and quantum mechanics only applies at really small scales at very high velocities and small masses. So there's no practical need for these two to be reconciled unless you're looking for the sort of grand synthesis theory that unites everything under one beautiful equation. And before that can be done, this problem between general relativity and quantum mechanics is going to have to be resolved. How much time do we have? What time is it?
Breakfast is at 6.
It's quarter to 9? I'm sorry. Okay, well, I had the whole second half, but maybe we could do it another night. I don't know. I'm sure people are falling asleep when full stop.
Probably something you were going to cover in the second half. In the Baha'i writings, it refers to fixed stars.
Yeah.
And either there's an Arabic or Persian definition of fixed that's different from what I conceive it to be, but how do you reconcile it with the expanding universe?
Oh, I don't think by that he's necessarily meaning that they're stuck in space, but rather that a fixed star being. If you look at the sky, you see some of these stars are moving, but they're not really stars. So a fixed star could just be another word for star. I don't think it necessarily means a particular class of star, but rather a fixed star. You say it's fixed because the stars don't move, whereas the planets do.
So you're defining as not being fixed.
Yeah, I'm basically defining it as not being fixed. I mean, I think by fixed doesn't necessarily mean it's sort of pasted up there in the sky and it can't move. That would be contrary. This is where the principle of unity of science and religion comes to the rescue, because any interpretation of religion which runs contrary to science is superstition, so one can safely discredit it. It could be a language problem. So what should we do? Should we reschedule for? I don't know. You're the boss.
Or you could do part of an introduction and then.
Let me just summarize it, and then if there's interest.
Why we have like another one long again, rather than skip over something that we start rich?
It's all up to what you're able to sustain at this late hour.
How much more time do you need?
Options to people that can put their hand up.
Okay, let's take a vote. If I could do this, if I could wrap up in a half an hour, who would want to stay a half an hour? And who would rather I sort of do this as like a more full another session another night? Okay.
So people want to twice.
It's like being dualist or monist. I mean,
Yeah,
you have to reconcile stuff.
Okay, so next time it'll be a sort of, so just to outline what it'll be. Next time I want to talk about elements in the Baha'i writings that seem to say, to give positive information about the structure of the universe. And then try to interpret these in terms of this picture of modern cosmology that I've painted, and to try to sort of weave it together into an image of like natural philosophy from the point of view of the Baha'i writings, or at least those fractions of Baha'i writings which we now have access to, because so many of the Baha'i writings on these sorts of subjects are as yet untranslated. So we're really dealing with a very small piece of what later generations of Baha'i thinkers and scholars are going to have to work with. So that's the plan. When should it be?
Yeah, I suggest that you can just email me who would like to come for next time, because I don't think we have to go through the same process like with somebody sending out an email and all this. So if you are interested, just let me know. And Stephen, what day is the best for you? Is it Tuesday?
Tuesday's fine. Wednesday's not good, but everything but Wednesday.
Next week?
Next Tuesday?
About Monday.
Monday?
As long as you like to report.